An H2 region is a cloud of hydrogen gas that has been ionized by ultraviolet radiation from nearby hot, young, massive stars. That makes it a glowing zone of ionized hydrogen pointing towards recent star formation. But what happens when a newborn massive star switches on and its radiation starts carving an H2 region inside a dense molecular cloud? That is the moment when stellar feedback becomes real. Hot ionized gas expands, the surrounding material is pushed and heated, and the next generation of stars may be born. H2 regions are perfect laboratories for star formation, but only if we can measure what the star is expanding into, that is, the dense molecular gas in the parental cloud. In a recent paper, Sawar Khan and colleagues, among others, Ivalu Barlach Christensen from the Max Planck Institute for Radio Astronomy, studies exactly this by using paraformaldehyde as a practical probe of dense gas conditions around H2 regions. The paper is entitled Exploring the Interplay Between Molecular and Ionized Gas in H2 Regions, and it's published in the journal Astronomy and Astrophysics on February 18, 2026. The goal is straightforward: to constrain the gas temperature and density in clumps associated with H2 regions and then relate those to what we know about the ionizing gas and dust. To build a consistent dataset, the team observed 61 H2 regions with the Atacama Pathfinder Experiment 12-meter telescope or APEX telescope, targeting several spectral lines formed by paraformaldehyde. The group fit the spectra and then used non-LTE radiative transfer to infer the physical conditions of the dense gas. LTE, or local thermodynamic equilibrium, means that the gas is dense enough so that the collisions happen so often between the molecules that the energy is set by the local temperature as if it was in equilibrium. Non-LTE radiative transfer, on the other hand, refers to the case where collisions in a thin gas are too rare to establish equilibrium, so that one has to include a more complex model of how the gas interacts with light. 3 takeaways stand out. Firstly, the dense gas around the H2 regions span a remarkably wide range of conditions, with, for example, temperatures ranging from about 34 K up to 265 K. That is, from extremely cold up to just below freezing. In other words, the environment is not uniform. Secondly, in 57% of the sources, the paraformaldehyde emission splits into multiple components and are consistent with a more turbulent, strongly stirred gas. Thirdly, when the authors compare molecular gas and dust to the ionized gas properties, it points towards the star itself being the main driver of the system. Across this sample, the neutral gas pressure is systematically higher than the ionized gas pressure, suggesting that the surrounding molecular material can slow down H2 region expansion, though the authors emphasize that confirming true confinement needs new and higher resolution data. Check the link to the paper in the description below, and remember to like and subscribe.